Now, our next speaker, who is jumping in because we needed to change a little bit of the schedule at the last minute, he said that this talk is actually not a full 45-minute talk, which is a very convenient situation for us, because he's going to end at a certain moment in between his time slots. At that point, we're not going to start immediately with the lunch. This is time for you to go to explore a little bit the aquarium or the zoo. And you also wanted to prepare a challenge, because you have one of his major passions, apart from Postgres, is to build up electric elephants, like the one that he's wearing now, electric elephant of the P-Day Lowlands. Here, this beautiful thing that gives on lights when it's in the dark. So what is the challenge that you wanted to give to people if they have a chance to go and take a picture in the zoo?
If it's working, well, the idea was, we came up with this sort of in the pub last night. The idea is, if you go and take a photograph of an elephant and share it on social media, you can win the chance to win one of 6 electric elephants. There we go. If we finish early.
So if you want one of those electric elephants, take the time to take a picture. You come with your selfie. You can put it on social media, and we will see it, and you can get your electric elephant on the registration desk. But come back on time for lunch, which is going to start at 12:30 according to the schedule. That one is on time. But now let's enjoy the talk of Chris, who is going to talk about fun stuff with UUID.
Okay, so yes. So first off, I'm Chris. I'm from the UK, if that wasn't obvious. I tend to kind of go around calling myself a bit of an IT jack of all trades. I've worked on quite a lot of different projects over the years, from search engines to industrial IoT systems that throw conrods out if the control software goes wrong, fun things. And pretty much a common thread across all of that is I have used Postgres in pretty much everything. I've been using it for about 20 years at this point. And this talk sort of came out of a conversation that I had at a Postgres London meetup with somebody, where I was discussing that I quite like using UUIDs for primary keys, and he had the viewpoint that that was terrible and it's an awful idea and you should never do that. So we had a bit of a discussion and a bit of a debate, and I kind of expressed, well, actually, I think there's an awful lot of value from using the extra space in UUIDs to do fun stuff. And this is kind of where this talk comes from. So first off, what is a UUID? So I'm guessing a few people in the room will already know what they are. Most people will be used to seeing it in this format, where it's a 34-character string. So this is actually 16 bytes of data encoded in hexadecimal. So that's really all it is. It's a 128-bit number. It's nothing more complicated than that. It's just 16 bytes of data. But there is some special bits in there. So there are 2 nibbles. So a nibble is 4 bits, which specify the version of the UUID and the variant. And if we look closely at this kind of big long string, we'll notice that this version field is a version 4 UUID in this particular example. And in this particular example, also, if anybody's good at remembering the ASCII table, you can work out what that UUID says. And in this particular case as well, we have this version 4 UUID, and this is also got a subproperty called a variant. The variant property varies based on all the different versions, so it's not consistent or standardized. UUIDs themselves have a whole bunch of different RFCs. They're not particularly the very early kind of versions that come from like the 70s and 80s have kind of been superseded, and the most up-to-date RFC probably that's used roughly everywhere is kind of 5962, which mostly focuses on specifying this particular version for UUID, which is what everybody uses because it's random. So if you use the function in Postgres to generate a UUID, gen random UUID, it's going to return you a version 4 UUID, which is basically 120 bits of random data. So how do we go about using these in Postgres? So it's not any more complicated than just a other column data type, right? We can use it just like we can a big int. So we can actually declare it as the primary key of our table. And this is an example from one of my systems where we have quite a lot of UUIDs, and the primary key is a UUID. So this is absolutely no different to if we were using a big int or a big serial or a int or a serial. So that kind of leads me on to, well, what's the bad side of this debate? Well, a lot of that comes down to, there's a very simple point we'll start with, which is it's twice the size of a standard 64-bit integer, right? So you're going to use a bit more disk space. But realistically, 2025, not really a problem. However, what becomes much more interesting is all the problems that the fact that by default, or the most commonly used version of a UUID, is randomly allocated. Now, to a large extent, it's more the random allocation of the ID that causes the problems as opposed to it being a UUID. So to some extent, I want to kind of expunge the bad press that UUIDs get. It's not about that data type. It is not a problem with the data type. It's a problem with the most commonly used version. And it is a problem with effectively randomness. Now, the fact that your ID is random, it's then inserted into a B-tree index as your primary key. There's going to cause a few problems, where number one is that by being randomly allocated, those different IDs are going to go to different pages in your B-tree index. So we end up with more index buffers that are in use at any one point in time than if it was a sequential ID, where in a sequential ID, it's going to consistently be appending to the same set of index pages. The other sort of trade-off with that is that you kind of lose the correlation between the ID and any form of temporal kind of locality. So if you're using a sequential ID, you pretty much guarantee that the higher the number, the more recent it is. And in most data systems, funnily enough, the most recent data is what's getting accessed most often. So by having our IDs that are randomly distributed, we kind of lose that connection between our ID having some connection to data that is most likely being used right now. And then there's another interesting side point where that kind of loss of correlation leads to certain optimizations in Postgres not working, because those optimizations are effectively trying to look at stuff in that kind of more linear way. So we're going to take a very simple test case to just demonstrate this problem. So we'll have a table, and in all these examples, the table structure is pretty much the same. We have an ID column, and we have a value. That value is just a text string of 500 bytes, just to create some space in our table. So that the idea here is we're just modeling. We have an ID and some kind of data in our row that's going to be usually fairly sizable, and we're going to do this with both a big int that's generated sequentially, a big int that's generated randomly, and of course, our UUID. So very simple test, very simple kind of setup and benchmark. And first off, let's just have a quick look at the size. So firstly, whilst our UUIDs are double the size, because we've, the ID itself is not really taking up a predominant chunk of the table, because that's actually our data that's taking most space, then we don't actually use too much more disk space when using UUIDs as primary keys compared to big ints. What we will see, though, is that the indexes are pretty much double the size. So our UUID index is basically double the size of our standard 64-bit index, which makes quite a lot of sense. At the end of the day, the actual physical data is double the size. What's kind of interesting is that the randomly allocated 64-bit integers are also bigger. Now, this particular test, I'm not cheating and creating the index after I've inserted all the data, so you get a perfect B tree. It's meant to model real-world kind of use cases where you create your table and then you fill your data in. So it's kind of interesting that obviously if we kind of do go and run create the index afterwards, then even on random data, we can build more efficient indexes than if we insert data going along. But what becomes very interesting is if we take a very simple test case that we're going to use to kind of show the different properties of different encoding schemes. So we're going to just do a index-only scan. So we're going to do this by just doing count of the ID. And that's going to basically do a scan only on the B-tree index of all rows. And we're going to use good old explain, and we're going to use explain buffers because we want to see the number of shared buffers that are hit by doing that index-only scan. So if we do that on our first example where we have a sequential big int, we look up about 27,000 buffers. So that's 8K blocks that Joseph's just been talking about. However, if we do that on our UUID example, we're hitting almost 2 orders of magnitude greater. We're hitting 9.5 million shared buffer hits. Now, this isn't necessarily going to slow stuff down always noticeably, but it is Postgres having to do an awful lot more work, having to constantly go and look up different buffers in shared buffers. And this is happening for one kind of reason, and it's down to that kind of loss of correlation. It's because we're using so Postgres' indexes doesn't have visibility information in it, that a row is within or outside of this particular transaction you're currently in. So to be able to check the visibility, we either have to go and look up that buffer in the heap and check the xmin, xmax on that particular record, or we have optimizations called the free space map, the visibility map. So we can actually go and look up in a bitmap that page is entirely visible to all transactions. Now, that optimization breaks down when you lose that correlation between how the index is structured and how the data is effectively structured, and that kind of randomness. And we can see exactly the same problem, more importantly, if we use randomly allocated 64-bit integers. So, conclusive evidence that this is not a problem with UUIDs. Okay, so I've kind of explained all the bad side. Now, the other part of the debate is, well, why on earth do you want to use them? And I think there's quite a lot of reasons. So, I tend to do quite a lot of web development stuff. And so many web applications, including our own conference management system, exposes sequentially allocated IDs. So if you want to go and look up speaker photos, you can just increment the ID on the URL and it will keep going, right? Now, that in itself isn't inherently a security problem. However, guessable IDs does kind of lower the barrier to a lot of things. And one thing that is good about UUIDs is, whilst it's not perfect security and it's more security through obscurity, it is a hell of a lot harder to guess a randomly allocated 128-bit number than it is to guess a sequentially allocated integer. So this is one of the reasons I quite like using them, because it gives you a level of inbuilt security in your app with absolutely zero effort and cost, where if you kind of want to follow some of the OWASP guidelines of how to do it all properly, it's actually very convoluted and reality why nobody does it. Now, the other thing, and this is where we'll start getting into more of the fun dimension, is 228 is quite a large number. So we can actually use them to do fun stuff. But before that, the other problem I dislike with database sequences is that they are database generated. So you have to go and ask the database to give you an ID, either by inserting the data and then returning an ID, or by just requesting it directly from the sequence. So you've always got a round trip if you're inserting multiple records and they're all correlated. So for example, say you're inserting a subscription with some transactions against it. You've got to insert the record to get the ID back and then do another set of inserts, which require you either writing some very complicated queries or stored procedures, or having an extra network round trip. Now, the thing I quite like about UUIDs is I can generate all those UUIDs in the application. It's by nature of them, they are mostly guaranteed to be universally unique. And I can generate those IDs on all the nodes in my cluster. I don't have to go and request it from certain things. I don't have to worry about stuff being in sync, etc. And I can do it all before I go and insert data. So it's actually really useful in a whole bunch of different scenarios and applications than having to have all your IDs issued by the database. And that other side of them being universally unique then becomes quite useful if you ever end up with distributed kind of geographically split systems. Actually, the fact that those IDs are very unlikely to collide makes it very easy if you want to then either move data around or join data up into, say, an analytics system. So it kind of simplifies some of those kind of sharding and migration strategies. But the really fun thing I like doing is using those 128 bits to encode information into them. So the way I see it is I have 16 bytes to play with however I like, because I don't like following rules. So all of my applications pretty much encode information such as, based on different projects, tenant information in multi-tenanted systems, potentially like cluster information in sharded systems, some form of partitioning information potentially. And sometimes as well, it's useful to know that this particular ID is this object, that particular ID is that object, right? You know, it's nice to know that this is the ID for an orange and this is the ID for an apple occasionally. And so if we take a very simple example here, so we've got this nice indecipherable ID at the top, and then all we need to do is bitwise OR it, right? So we're just going to OR all the bits. And now we've made something where I've got a tenant identifier at the top. I have an object identifier with inside that tenant, and now I have the ID that I use everywhere that gives me those 2 bits of information really easily. So in this particular example, right, we are still allocating this ID roughly randomly. But the tenant ID is a lot more stable. So the kind of the MSB is actually changing less frequently. So even just doing this solves half of the B tree problems. But we can go even smarter. So this was an application I was working on recently where we actually encoded into the IDs. So these were the IDs that we sent to third parties and everything that correlated to a specific like insurance claim. And we encoded information, and the first bit was effectively the kind of what I called the chunk, which was a tenant and a quarter of a year. So we had space for 400 quarters roughly. And we actually then inside that had a time offset where we could actually go to 5-minute precision. So we could know the 5-minute slot within that quarter of a year that ID was generated. We then had information about what particular type of object this was. And for situations where we had like child objects, what particular sequence it was. So we can actually just from the ID know that this is an insurance claim and it's the second claim against a policy. And then the last part is all just a completely random 64-bit ID that is kind of there for stopping stuff colliding and kind of security. So this is the fun stuff I like doing. Now, the interesting question really is, can we get the best of both worlds, right? So can I have all my fun with my IDs and not suffer all the consequences of stuff being randomly allocated and all the index downsides? So there is a standard that's finally got standardized, and I believe Postgres 18 has support for it. So UUID v7, which is effectively just time prefixed random IDs. So if we go back to that very first slide, and I've colored it in gray here, you'll notice that the version number is now 7. And there is some variant information that is then specific to version 7, but we won't go into that. But effectively, the top 48 bits are a timestamp, and the rest is completely random. And just that one change is enough to solve all of the problems with indexes, because the top MSB is slowly changing and now has time locality in it. But that's too simple, right? I don't want to do that. So let's come up with my own scheme. So I came up with my own scheme called, I've decided to dub fluid, flexible UUIDs. And so part of the V7 spec is also introducing a new version 8, which is basically describing version 8 as custom, you can do what the hell you like. So I like those kind of rules. So I've kind of got a few different versions, so that you can have 4 variants, right? So I've got 4 different variants of my kind of custom scheme, but following the kind of same basic principle that the top MSB is time. So we have a timestamp there, so we keep some form of linear order, and we then kind of play nicely with our indexes. I then, on a multi-tenanted version, have tenant identifier in there. I then have some additional kind of information I can code about, say, what the object type is, and then we just randomly have the rest as completely random. So there's another version as well where it does come with more rotating blocks, because even sequential IDs aren't perfect for indexes. So we also have an option to effectively just keep rotating around in X number of months the kind of IDs. So let's take this example and then run the same query I was doing. And we can now see that, so in my particular instance here, where this is a UUID where it is time prefixed, randomly allocated. So we still got like 80 bits of random data in this ID. And rather than, we're hitting a few more buffers, but it is nowhere near the catastrophic problem of completely random. And the same in the multi kind of tenanted situation. We kind of have slightly less data in that particular case for the timestamp. So the number of buffers we hit does get worse. So there is a bit of like how much time information to encode into the ID does change how effectively Postgres' optimizations work, and therefore kind of dictates actually how good or bad this particular approach does or doesn't work. So obviously in this instance here, with using the multi-tenanted version, we have that shorter time section. We do hit almost double the amount of buffers, but you've got to take your trade-offs, right? And it all depends on how many tenants you have, etc. as well. And then say different schemes kind of get the different kind of processes. So by using a bit more time information, we kind of then actually solve the problem slightly better than having less time. So it's a bit of a trade-off of how much ID space you might want for having tenant information versus how much you might want for time information. But you've got 128 bits to play with. What more do you want? And then I thought, let's talk about the kind of actually insert performance. Actually generating these IDs and inserting them, are they actually much slower? Turns out, not really. At the end of the day, the bulk of your kind of insert cost is inserting the data of your row, not the ID. So in this particular instance, so this is a benchmark from a Java app inserting 10 million records, 500 bytes of data per record. Obviously, our sequential big int is the fastest, but actually all of our UUID schemes are not depreciably different from just a random 64-bit integer. And in fact, some of our schemes are ever slightly faster than using Postgres' built, using a pure random. But at the end of the day, actually, insert performance isn't that much different than the kind of best case anyway. So in other words, don't worry about it. Right, now we can get onto the proper fun part. And it wouldn't be one of my talks without some good old procedural SQL. So this is a bit of demonstrating the fun things we can do with Postgres and the fun things we can do with these IDs. So can we generate this random ID scheme in pure SQL using Postgres? And the answer is yes, we can. And it might look horrific because all it's doing is really a lot of string chopping and hex encoding, but it works quite well. So effectively, we cheat slightly by just using Postgres' gen random UUID to get us the base random, and then we lop off everything we don't want, and then just concatenate together the data we do want, encoding into hex, and then cast it to a UUID. I did do this talk at PGConf.de, and a few people said, oh, have you tried benchmarking it with, say, using the bits versus that? And the answer is no. I will come on in a bit to actually, I did write a C extension. Surprise, it's not actually that much quicker than just doing this horrific thing. But of course, like, I work with a team of developers, and I shall say that not all of them had the same level of appreciation for this fun that I did. So we need to give some rules, right? So how can we actually decode and extract this information so that, more importantly, I can then go on and add a check constraint? So first off, actually, how do we extract the information? So I'm still a bit irritated. Postgres doesn't have a parse hex function. I really should try and raise a patch, maybe. But the trick here is we have to just use PostgreSQL this time round rather than pure SQL, and use the kind of select X trick. But the nice thing we did was, because we laid stuff out so it all aligned to nibble boundaries, all we have to do is use right and left to take out the particular hex digits we want, and then convert it from hex to an integer. Again, actually not that complicated, really. So now we've got a function that can check the version of a UUID. And now I can do this, so I can add a check constraint to the table that says, you're only allowed to insert UUIDs in this table that meet my own custom scheme, so that if you try to insert a random UUID, you get an error message. And now I'm happy, my developers less so, but hey-ho, they'll learn slowly. And then we can go, slightly further and actually say, well, let's extract the variant information as well. So all we just have to do is pick out a different nibble. And then we can update our check as well to say that, I only want IDs of this particular scheme in there. So because I've got different variants, some that specify it's a multi-tenanted ID, I can now enforce at a table level that my primary key is guaranteed to have tenant information in there. And now we can kind of play around with time and have some fun with that. So the first half of the first kind of prefix of all our IDs is actually a timestamp. So again, we can write a function that takes that ID, extracts the timestamp, and now we have a way to get the time out of an ID. But it's important to realize that because the time is in the MSB, so the most significant bytes, we can actually, they are in order. So a lower timestamp is a lower UUID, and a higher timestamp is a higher UUID. So we can actually do something like this, where I don't necessarily need a created column on my table to know when a row was created. I actually have a level of precision in the ID itself to know when that particular row was created. So just doing this mad thing here that's very hard to read, that's kind of searching for 1 month in January this year. Might not look like it. But now we know we can do that. And that will work with UUID v7s. Now we can do that. It means we can actually partition our tables by primary key based on time just using a UUID. I think that's pretty cool. And I believe some people are doing that, using UUID v7. But to make it a bit more readable, I created a function that you give it a timestamp and it generates the ID for it. And now you can just write something like this. So create table partition of 4 values from this time to that time. And you know that that table will always have rows that were generated in that between those particular times, just using the UUID primary key. Now we can go a bit further as well. So because I'm not just using time-based, I also have tenant information in there. So the really obvious use for this is actually just inside my application. So let's take a simple example. I have 2 database clusters, and I put 50% of tenants on one, 50% of tenants on the other. Then in my application code, whenever I'm looking up, load this particular subscription, I've already got the primary key, but I can pull the tenant information out of that. I can then look up what database it's in, connect to that database. So pretty kind of common tenant kind of sharding strategy. The advantage here is I don't need to have a magic tenant ID. It's already all in my single ID. But we can go a bit further. We can do that in Postgres, right? So we can also extract the tenant information in Postgres, which then lets us do stuff like this. So, filter, find me all rows in a table where the tenant ID equals a particular tenant. And we could also say, well, let's make that slightly quicker so we can use Postgres's expression index support to actually just create an index on the result of that particular function. So we can actually do that and still have good performance. Now, what I thought would be really interesting is, well, can we partition by tenant? And the answer is kind of. So we can actually do this. So we can do a list partition by the result of that function. And then we can create partitions with that. And especially have a default partition, because we're doing list partitioning. And therefore create partition for our tenant. And that does all work. The only problem is Postgres isn't smart enough to know it should call the function to then work out the constraint exclusion. So it will just scan every single partition you've got. So we can do like 50% of it. We just can't do it fully yet. Maybe that will change in future versions of Postgres. And then if you thought this rabbit hole couldn't go any deeper, well, so I alluded to this a bit earlier. I decided to write a C extension. So this does exactly the same as my horrific string manipulation to build an ID, or in this case, sorry, to extract time. And I've got another one that will do it to extract the tenant information. And we can obviously, compile that code, register the functions, and we'll see that actually it's nowhere near as fast as you think. That actually using C to generate the functions is only 25% faster than my horrific string manipulation, which really quite surprised me. But yes. True, I did not select it, just select count. Oh yeah, sorry. The question was, did I test this just on select count, or basically just generate series? Maybe would be another way to do it. I might have done, I can't remember, but yeah, I probably did also test the insert performance. So yes, that's probably a good point, and maybe I should try that again. But I guess my point would be, I'm trying to keep the benchmark consistent with what I was doing all along. And actually, in most cases, I am generating the UUIDs in my application code, so I don't really use this very often. But what was interesting is that the extra effort to write a C extension and install it, on those few times I do actually generate a UUID in the database, wasn't really a problem. I guess to explain things a bit better. And with that, we said it would be slightly shorter. So any questions? Am I completely lunatic? There's one.
Okay, one question here first.
You started off with saying that you can use a UUID created in the app and then have no back and forth to the database.
Yep.
So, and it has no collision.
Theoretically.
Well, theoretically, no collision. So what happens if you use your fluid IDs or UUIDs v7? Then the chance of collisions, they are going up. So what's your thought about that?
So yeah, the maths is all basically the same maths as the common birthday problem. And obviously, the less space you have for random, the more chance of a collision. But in those time particular UUIDs, right, you've got to now you've got less size to find a collision, but that collision has to happen within like a 5-minute time span. So I personally, I don't run like huge, web scale, etc. So in all of my normal business projects, I have never actually hit a collision. If you do hit a collision, your primary key is going to catch it anyway, so it's not a problem. Unless you're maybe got two completely geographically separate stuff where you've not got like one index. But yes, there's always a chance of a collision. It's just extremely unlikely. And I've never seen it happen. Any other questions?
Yes, another question there. Mikkel.
Give you some exercise, Boris.
Yes, since you're on the topic from IDs, that is, you have also a smaller one. This one is the UUID. You have also the Snowflake ID, and I thought, did you, how it's called, investigated on this topic also?
No,
or is it too small space to comfort you?
For the stuff that I been doing, I kind of prefer the extra size. So the Snowflake ID is basically a time-bounded but randomly generated 64-bit number. And yes, it would still satisfy all the conditions, but you wouldn't have the problems that you get with pure random data. So it is better than just a randomly allocated 64-bit number. For my particular use cases, I've always wanted the extra space and the ability to have more information in there. And the other problem is when you do start bit masking stuff, the space shrinks quite quickly, quicker than you think. And sometimes, I do want more than 32 bits for a tenant ID, for example.
Yeah. And the second one is the 2 8s. Those are free. Why are you still sticking on it then?
What, sorry?
On the UUID, you have the two fixed positions, the
Yes.
version and
Yes.
the variant.
Yes.
And my question was, why do you in Postgres you can also leave it free as an extra space?
Yes. I would argue you probably always want to use the version because it is actually useful information. The variant, maybe not. So yeah, if you do use that extra nibble for extra random data, then you kind of lose the ability to say that this is a random one or not. So I would say, for me, it's still useful to know that, which is why I kind of don't want to use that extra space. The variant, yes and no, sometimes you can do that. The rules around it get more complicated because most of the specs don't say you can use all the 16 values, so you can't use the full 4 bits. Which is why you only get really 4 variants you can use in a lot of the standards. But it all depends on compatibility as well, right? If you've got to send this ID to another system that might be parsing it, following a more standard, following a standard compliant parser, then I would argue you're better off trying to follow the standard than just squeeze a bit more data in.
Thanks.
Okay, so this has been obviously a very good choice for to talk about UUID based on the questions that we have got here. Chris is also going to be here the rest of the day, so if you have more questions, please reach out to him. I have some questions about distributed UUID, which is, but I'm not going to do it now because I want you to have a look at the zoo. We have a little bit of time now. You can roam wherever you want to go. The food is going to start here at 12:30. If you come a little bit later, it doesn't matter because then we avoid the rush of everybody trying to fight for food. Yeah, we have evolved a little bit from that period of time. So you have time from 12:30 and 1:30 to get your lunch. Before that, you can go and take a picture of yourself with the elephants, and you can get a chance of winning one of those beautiful electric elephants made and donated by Chris. What he hasn't done yet is key rings. So that's why we are going to give him a key ring and thank him for his especially nice talk. So thank you very much, Chris.